write your tests better and doing it with less work doing it. So I started out as a theorist, so let's start with some theory. Why do we write tests? It's a lot of work. I ran the numbers on Flutter itself, and it's actually more tests than the implementation, including all the docs, those lovely API docs on the implementation side. And that can happen in other code bases too. We spend a lot of time writing tests and updating them, maintaining them. Why do we do it? Well, it's to catch bugs, right? Can you hear me? I see. It's to catch bugs, right? And yes, is it to catch bugs? You write code, you write some code, then you write the tests, and you find the bugs in the code you just wrote. I think it's sometimes that, but you are running your code, right? You're trying it. And really, I think for maybe most of the code we write, most of us, that's the easier way to find the bugs now. You fire it up, you play with it, you like poke the button, no, it doesn't work. That's faster than writing the test that like exercise it doesn't work. So sometimes that's important, but I think actually for most code, it's not the key thing. What the tests are really for, the real payoff, is in the future. They find when stuff breaks later. They find regressions. They find when somebody made some other change and they didn't realize it interacted with the change you did today, but it did, and the test is what tells them that, so they can not break it. As we say in the Flutter upstream project, the point of a test is so that the purpose of tests is so we don't accidentally revert your change. That's what the test is about. So tests are about the future, finding future bugs. So let's look a little more detail at that life cycle, that timeline. So you write the feature, you write some tests, you pay a cost of writing it, and you pay a cost of somebody reviewing it. And then you run the tests over and over and over again. They don't do any good if you never run them. You spend compute resources in CI, probably every PR, and you sit there waiting to see the results as you're developing. And then later, somebody builds some other feature and changes the code, and it accidentally breaks your test. And then there's another cost, which you got to figure out what's going on. It broke the test. Is that a problem with the test? Did it need to be updated? Is it a problem with the change I just made? And maybe the answer is it's a problem with the change I just made, and that's what it's all about. That's the only reason we write these tests, the main reason. Or maybe it's the opposite. The problem was only in the test. That's what the change needed to happen. That's another cost. You already had to figure it out. Now you have to update the tests. And in a lot of code bases, I think that's actually that's the biggest cost of tests is you got to update it again and again and again as the UI changes or other things change. And so a lot of this talk is about how do you reduce that cost as well as the others. So here's all the costs on one slide. This talk is about better tests with less work. We're going to lower those costs. And so that means, well, they should be easier to write, less of that cost, easier to review. They should be cheaper to run. They should have fewer of these failures you have to diagnose, except the ones that are real, the ones that are the point. When it does happen, that should be easier to figure out what the deal is, what the story is, and then easier to update if that's what you need. And of course, you want to catch more bugs. That's part of being a better test. And so the things I'll talk about how to do that, excuse my slide craft on this one, but you want to tell a clear story, a clear narrative. That's going to help people understand it, the reviewer, people diagnosing it later, people need to figure out how to update it later. You want it tightly focused, which again helps it easier to understand. It also means less code, makes it easier to write, easier to update, less code to run, so it's cheaper. And it helps you write more of them because it's less code again, so you catch more bugs. You want to take the parts that are boring. This is a key part of accomplishing that clear narrative, telling a clear story. A key part of getting that tight focus is take the parts that are boring and move them out. That also makes it easier to update because you've got fewer places to update those boring parts. We'll get into this. You want to write them at the right layer beyond the binary of unit tests and integration tests, which I'll get more into. And there's a couple of packages that I recommend. They're both from the Dart team, the fake async package and the checks package. They help you write tests that control more, that are clearer, and I have some specific suggestions to make on how to use them. So the 6 techniques they'll talk about, the first 3 of them, you might wonder, did I just walk into a writing seminar? I thought this was a tech conference. And the answer is yes, you did, at least in part, because coding is writing. The tests you write today, they're going to be read by not only computers to run it, but by humans, by somebody reviewing it tomorrow, by somebody else on your team next month as they broke something, got to figure out what to do with it. Yourself next year, and you got to add similar tests like it, understand what these tests were doing. And so clearer tests, they reduce all of those costs. Not every cost, they don't make it run faster, but they reduce all of these costs of humans understanding it. And they increase the payoff, because when the test fails, if the person can't figure out what the story is this test is telling, they may not get the signal it's telling them. They don't realize that it's telling them there's a bug in the change it just made, and then the test didn't accomplish anything. It didn't deliver its mission of explaining it. So let's get into the concrete. Concretely, how do we do these? So you made a change. It broke a test. This is what you see. What do I do with this? The key thing you want to figure out is, did this test, is it telling me something? Or do I just need to update it? So maybe 48 is the right answer now. The test is telling you that something was supposed to be 44, but it's actually 48. Maybe the change I made means it should be 48, or maybe it doesn't. Maybe I did something wrong. I need to figure it out. So okay, the line that failed at looks like this, great. And then what happens a lot in a lot of code bases is the rest, it looks like this. It says things should work, great, thanks. And there's a thingum, it's got text, it's size 15, it's a frobnitz. And the warble has an asdif of 7 and a warble of 3, and there's 20 more lines that go on like that. And then the answer is supposed to be 44, great. Why was it 44? And you got a reverse engineering problem in your hands. And so now you're going to pay those costs of figuring out what it is that this test is doing. And you may miss the signal, so you don't even get the payoff, depending on how much time you spend on this reverse engineering. And so if we were writing this test, what should we do to make this less reverse engineering problem, to lower these costs, to increase the payoff? Well, instead of looking quite like this, we could make it look like this, where there's a couple of things going on here. One, that answer, it turns out that the reason it's 44 is double the size plus the asdif. And you can just say that in the code, right? You pull out those details as local variables. And then the connection is very clear. And then the other thing is that, it's double because it's frobness. And you can say it, the one thing we said in code, the other maybe it's clearer to say in comments, a nice short to the point comment. And also the description, the title of the test helps tell the story. And so now it's a lot clearer what story this is telling. And when we made the change and now it's actually 48, we can ask these crisp things that were supposed to happen, are those things still supposed to happen? I can compare, I now have in front of me the intentions of the person who wrote the test. And so I can compare those intentions against the ones I have now. And it's a much more defined problem. It's not a reverse engineering problem anymore. It's a forward engineering problem of, do I still mean these things, or do I want to change them? And if I do want to change them, it also it makes it easier to write the update, to write what the new version of the change should be, because I just, if I change the size plus asdif, it's no longer what it's supposed to be. I swap in the new formula it should be. So this is a test with a clear narrative. The next thing, which supports a clear narrative, is making it tightly focused. And I wrote that example compactly so it fit on the slide. But in reality, of course, there's a lot more detail going on. And that's true even if, again, only a few of these details were part of the narrative. Now that we're telling now the narrative is clear, we can see that only a few of those are actually part of it. And so tight focus is about taking the details that aren't actually part of the narrative and getting rid of them, which can take a couple of forms. One is if the details really don't need to exist at all. So for example, maybe this thing, if it's got 2 items in it, the items are 1 and 2, and the reader's got to go through that just to like read this test, understand it. And what if they didn't? What if there were no items? If that's possible, if like a thing doesn't absolutely have to have items, you should do that. Just make it more boring, less to see. Some details you can't just eliminate. Maybe, there's always a warble and it can't be 0. It's got to be like more of a number. And when the details do have to exist, but they're not really, again, part of the narrative, they're not part of what the test is about, then the thing to do with those is extract them. You move them out of the test case because they're not part of what the test is about. You move them instead to a helper function, a test helper, perhaps. And so now, instead of saying it's an asdiff with a warble of 3 and a bunch of other stuff, it's just a global with asdiff. And all the rest is implicit, which is good as long as it didn't actually matter. All the rest is implicit, and it's over there in this test helper, which takes care of all these details that are boring. They're not part of the point of this test. So before we had a test that looks like this, and then it's so much simpler when we extract the boring details. And this is what the test can look like. It's got the same narrative that we showed before. It's got the size and the asdiff, and provenance is true, and that's it. It doesn't say anything else. And this is now very short to understand, very crisp to understand, easy to diagnose when something goes wrong, easy to update if you have to update it. This is what a test can be. And you don't want to go too far, so you extract the boring parts, but not the non-boring parts. If the size here, 15, that was part of what the reader needed to understand the test. And if that gets extracted like this, then like you look at this and you're back to a reverse engineering problem. Like, why is it 15? If the answer is, it's 15 because the test thingums are always size 15, that's not very helpful. You got to go, dig and guess that. Don't make the reader look it up. Even if 15 is reasonable default, put it in the test explicitly if it's something the test is depending on. So you extract the boring parts, makes it easier to read. That's cheaper. It makes it easier to diagnose. It makes it easier to update. If the every time there's another field on your global datas, instead of having to go and add it to every single test that has a global, you just add it to that test helper, and you add it to the handful of tests that are actually about that new field. But for all the tests that didn't care about that field, you add it once to the global data, the test helper. Again, that lowers the cost of updating. And it makes it easier to write more tests. Every test is so short and so crisp, it's just a few more lines to have this other test. Now you've got both these tests next to each other, and it gives this contrast. You see exactly, yes, it's double because it's twice this other test to compare it to. You can even see them, they here fit on a slide. They'll certainly fit in your IDE, like on your nice development machine. So you can see them, compare them as you're developing. So that's clear narrative, a tightly focused test where the boring details are extracted, but only boring details. So far, we've all seen this in the context of slide code that fits in a slide. A lot of the value of these techniques really comes when things get bigger than that. And so let's do some real world examples. So I'll tell you a bit about the app that my team has built, because I'll see examples from that. So it's called Zulip. It's a team chat app. It's got users, they send messages to channels. It competes with Slack. That's a team chat app. So it's got a server backend. That's where the data comes from. That'll come up in the architecture. It's organized team chat. So the messages that are in channels have topics. That comes up in the test as well. And that's, by the way, the key thing that people tell us they like compared to Slack. It makes it less chaotic to use. And it's 100% open source. So you can, everything that I'm showing you from our code, you can go see what that code looks like. Look it up on GitHub, Zulip Flutter. And so here's some real code from Zulip's tests. I talked about extracting boring details. There's a lot of boring details in a user object. And this is the actual code. In real life, it's taller. It's got more new lines. But the only thing I did to put on the slide is reformat it. So it's got all these details. You would not want to be doing this on every single test that needs a user, which is most of the tests. But it's nice and extracted like this. And there's a few bits that are a little bit interesting from a test perspective. When you just make a user, it generates the user ID. They got to be distinct, right? And so it can't just have one default, because that would be pretty unrealistic to have all users have the same user ID. So it generates them, and you could make it sequential. We made it random to help like avoid any kind of like weird test interactions where it was secretly depending on the fact that they're sequential. Random but increasing, just in case like some things do care about the order, because that shouldn't really matter. There's a lot of things that don't have reasonable defaults, which is why the constructor doesn't have a default. Like you can't, like there's no default name that makes sense for a user, right? There's no default email that makes sense. And so it's only in the test code that you can fill those in as defaults and not have to specify them when you construct them. And here's a random, one of many, many tests like this in our code base that uses it. So the convention that we use, I like this convention. We import it as EG, as in, abbreviation, Latin abbreviation of the dots, EG. So there's an example user, eg.user, and in this particular test, it needs the user to have the moderator role instead of like normal member role. And so it says that, and it's it's testing that the moderator doesn't have permission to do what only administrators can do, because administrator is a more privileged role. And it actually, one nuance here again, you extract only the boring details. If you actually just if you didn't pass the moderator, the test would pass, because a normal user doesn't have the permissions either that an administrator has. But it's actually, it's important, the test is comparing the permissions, right? And so if you just let that implicit, the reader would have to know that it's a normal user doesn't have the permissions. And so again, you make it explicit, even though like the test would pass if you didn't. It makes it easier to understand. So there's our real test helpers. And I'll have more examples from our code base as the things go on. Let's see let's talk about the right layer to write things at. This is the other key piece of testing theory that I have. So you've probably all heard about integration tests and about unit tests. And should I write integration tests, or should I write unit tests? And as you can maybe tell, I don't love these terms. I think that that's too much of a dichotomy. But so an integration test that classically means you got a real device that is running on, or at least a real simulated device. You got a real server back end, if that's what your app has. It's expensive to run. You got like a bunch of hardware, a bunch of compute resources. They're slow. It's a real pain. You want to sit there waiting for results. They're flaky because like you got the network connection to the thing, you got the device, and like the device is, it's constantly, that's not always online, or things don't start up in the right order because they got time to start up, and you're constantly maintaining it. It's costly. So it's, you do have to do these sometimes. There's some things that you can't really test in their way, but you do not want to do this any more than you absolutely have to. It can't be the main way you test things. A unit test, there's a very classic way these look like, where, okay, you got a class, it's got a method that does some things, and your unit test, it mocks out the stuff the thing is using. And this is an example if you use Mockito, for example. And you can, as you can maybe see, the test, it's just the same thing as the implementation, only in like testy language. Right? It's saying the exact same thing again. And if you've got tests that look like this, it's, what happens when the test breaks? Well, I guess I'll get to that in a moment. So there's a good thing, which is these are usually cheap to run because there's no dependencies. But that's really about it for good things about these, honestly. Because they don't actually, I would say honestly, they don't actually work. They don't have much chance of giving you the payoff of the test. If somebody makes a change and then the thing breaks, well, what are they going to do? They already edited the real code, and they thought that edit was right, or they wouldn't need the test. And so the test code is it's saying the exact same thing again. So what is it? It's not going to tell them anything new. They're just going to make the exact same edit, only like style transferred into test code. And so it's nothing but costs, these like pure classical unit tests. So at binary, there's integration tests. They're expensive to run. They're noisy. They're full of like failures that aren't real. And a unit test that just like duplicates things. What's the point? I think probably a lot of us already, we're not writing these like classic unit tests. I think a lot of understand that you got to write something that's a little more meaningful. But I think I have something to say that maybe helps crystallize what they should be doing instead. And maybe a lot of you are already doing this already, but hopefully I give you even just a way to communicate it in your code reviews to your coworkers, which is you want to test at the interfaces that are stable. Interfaces that, by which I mean interfaces that are already committed to keeping stable. Interfaces where there's already a cost to changing them, where you're already constrained by compatibility. So for example, a server API, if you've got a server backend, that's always a little bit of work you got to do to deal with mismatched versions there. So that's already constrained by compatibility. Your database schema, you may change this all the time, but you got to deal with migrations, and you do. It's constrained by compatibility. If you're making a library on an app, then the API you export, that's definitely constrained by compatibility. People are depending on it. Even your UI, I think you can tell the story in this framework that you want to test things in terms of the stories of how people are actually using it, not the pixels on the screen, which the users don't care about changing in small ways. So you test at stable interfaces, and I'd say the reason for this is when you write a test against some interface, now that test is itself a cost that you're paying whenever you change it. But conversely, what it basically does is tell you when it did change. It's a signal when it did change. And so if you have an interface that's already constrained by compatibility, then those signals are a good thing. If it fails because it changed, great, that's the thing you wanted to know. It changed, I need to deal with that. And conversely, you got to deal with it. And so, okay, I got to update some tests. That's not even the hard part of dealing with updating this interface. You got to deal with like the things that are using it or the migration and so on. The test is the easy part. But on the other hand, if you write against a test that was otherwise an internal detail to your code base, now you're ossifying that interface. You're making it more work to change it, and you don't actually care when the interface changed. Like that wasn't a signal you needed. So you want to write your tests to stable interfaces that are already constrained by compatibility. And back to real examples, what this looks like in Zulip. So our app, it's like I think probably a lot of apps. It's got some UI code, which is made of widgets. It's got some business logic or a model. And it's got a binding to our like backends, our server backends. And so the three things along the top, those are the code that's in the app itself in Dart. And then down below, there's these layers we're depending on, right? Where they go to the Flutter engine, all sorts of plugins interacting with the underlying platforms. We got our database, and we got the server, which is it's also Zulip, but it's separate code base. And so I've drawn the diagram so that all these interfaces between the top and the bottom layer, those are the stable interfaces. That when we change those, for the ones that we do control, when we change them, we got to do some work to deal with that. For the ones that somebody else controls, we got to do some work when they change it, and they know that, so they try to not change it too badly. And so those are the interfaces we test at. So how do you do that? To test these interfaces, you need the test to be able to control them, right? To control what happened to the other side of them. And in other words, you need dependency injection, as it's often called. You need bindings, as Flutter itself calls them. So one thing we take inspiration from is the one that you're all using when you write your UI tests in Flutter, which is, Flutter calls it widgets binding. It's a class within the Flutter framework. I recommend taking a look at it. It's actually very interesting to see if you haven't already. For talking to the server, the Dart library, their standard library comes with this basically dependency injection layer, this binding layer, the client interface, and you can give a different implementation of that. And so when you run your tests, you run Flutter tests, it swaps out a different implementation of the widgets bindings. And you can swap out, and we do, a different HTTP client to be a fake one. And so we in our code base, we've taken inspiration from widgets binding, and we have and follow exactly actually what it says on docs.flutter.dev for how to test plugins, or code that uses plugins. We have our own binding that's similar to widgets binding, not quite as complicated. And we've used that also for our database, following Flutter's example of how it talks to the platform. And each of those bindings, they have a test implementation that runs in tests instead of the one that's running in the live app. And so test code, it controls that bottom layer. Those test implementations, it can manipulate. It pulls the strings as a puppet master to do what it wants. But it uses the real implementation of the things to the right. And so, for example, UI tests, to dwell on those for a bit, our UI tests, they're not unit tests of the UI. They don't use a fake model or a fake business logic implementation. They use the real implementation. They feed the data through the external API, the one that is constrained by compatibility, the one that's stable. So it's not a unit test, and that's good because it means we can freely make whatever changes we want to that top left arrow, the one that's the interface from the business logic. We can change those data structures internally freely, the ones that are implementation details, because we should be able to. But it's not an integration test, which, thank goodness, that'd be such a pain. Instead, they run locally, on the development machine. They're fast, they're reliable, not full of flakes, because of all those dependencies. And so that's why we do it. And so, again, that means we're feeding data through this API, and just to focus on the server API, that's fake HTTP responses, which this could be a pain to construct. Right? Maybe it sounds like a pain, and to update, when you change something in the API, you got all those responses, but we covered this, right? Those are the boring parts. You factor the boring parts into helpers, and we have. And so, one side of those boring parts is the details of sort of the HTTP layer itself. And so here's, again, what a real test looks like. There's this fake API connection implementation, and it's got a method prepare, which the real thing does not have. That's the test method, where it queues up this fake response, and it deals with so in this test, it's taking get stream topics result. That's the result from the get stream topics route on our server API, and that's the real type that's used in the live app, deserialized from the wire. In this test, it's constructing one fake, and this prepare method, when it gets that, and it deals with the boring details that almost all the tests have. It makes a JSON, and it sets up the HTTP response the same way the real server would. And then the next line is it calls back to a different part of the previous slides. It's one of this EG from the example data.dart. EG dot get stream type. It's an entry in that, and it just takes care of some of the boring parts that are in this particular bit of the binding. And so this ends up being, again, very concise and just saying the things it actually needs to say. It says the name of the topic because later it's going to use that same name. So that's a stable interface with the server. And a UI test has another interface, of course, which is the actual UI, the way the user is experiencing it. And so what does a stable interface mean then? I hinted at this before, but users don't follow a spec, right? Our server API has got a spec, it's got documentation. There's a very crisp thing it should follow. That's not how users casually using the app work. They don't follow a spec, but they do still have expectations that you're planning to meet in the way you write the UX, and that you have met maybe in previous versions. And that's what you test against. And that, I think that is, again, it's constrained by compatibility. If you change it radically for no reason, your user can be confused. You want to know when you're changing it. And so those are the terms you want to write the UI tests in. And so concretely, when you're using Flutter tests, that means instead of golden images, where possible, use widget finders and so on. There's probably a few things. If you're implementing squircles, you want golden tests for those, to exactly how those look. But aside from very few focused things that really are about pixels, all your other tests, they're about the functionality more than the pixels, and so you use widget finders. And with those widget finders, it's sometimes very convenient to use find by type, by the widget class name. But that's not part of what the user knows. They don't know what you're calling your widget classes. They don't know how you structure your widget tree. So for the most part, I think you don't want to use find by type, but use the text, the label and the button or whatever, or the text in the topic or the message if it's that you're showing. Or if it's an icon button, find it by icon or find it by the tooltip that's on it. So that's the stable interface for it all. Now, even if you write it that way, those things, they do change. They change maybe more than an API does, because your PM decides to tweak the label, or your designer wants a different icon. And so it's a pain if you got to go update tons of tests for that. But that is avoidable by, again, factoring out the boring parts for where they are boring. And so when you've got a test that is about screen A and it just taps button B to get there, then instead of having that test go find by the icon of button B, you write a function. This is what we do, at least, what I recommend doing. Write a function that's like prepare screen A. And use that in all the A tests. And give it a whole bunch of optional parameters for all the details of what screen A what data it should have on it or whatever it may be. And then that actual text of the button B or icon, whatever it may be, it appears only in that one helper as well as the tests that are actually about button B. And so now, updating B is back to being cheap. You just update that one helper, and that takes care of all those tests where it's boring, and you update the tests that really should care what the text is of the button because they're about that button. All right, so we're getting close to the end, and I'm getting close to my materials. So a couple of libraries I promised telling you about. So we've had bindings for the server API and for the widgets. What about a binding for time itself? So sometimes you have code that's got sleeps in it. It awaits like a delay of some time, and sometimes that matters, and so you want to test those too. But you don't want to sit there waiting for a second for that one test case to finish, let alone if it's supposed to wait for an hour. Right? That's never going to work. So you need to test control time. And there's an answer for this in the Dart standard library, or not standard library exact, but from the Dart team. There's a package called fake async. And so here's your basic way you use it. So this far, I'll have more later, but this far you can get basically from the README of the package. It's going to have something like this. Inside a test, you construct a fake async object, you call run, you pass it a callback. It gives you this, conventionally the argument is called async. It's a little confusing the first time you see it. It's not the semi-keyword async. It's just an ordinary function parameter. And it's got methods that just make time pass. And so in this test, for example, it's not really testing anything, but imagine that it was calling some function that did these things that it's testing. It waits for a second and then it marks the thing as done, and you can see it's waiting first, but after time passes, the thing is run. It's done. I do not recommend actually writing tests this way. I do not recommend writing them like the way that's in the README of fake async, because there's a pitfall that if you instead do the very natural thing that you would do if you weren't using fake async, that you just await for the thing to finish. The thing that you are probably already doing in all kinds of widget tests, because this is how widget tester and Flutter test works. If you wait it, the test will not work and you won't even know it until you go try to print debug something. The test just will not finish, but it won't complain. You have an await there, but the future never completes, and so the callback never happens. And so even though your assertion was totally bogus and could never have worked, you will not know that. So this is no good. The solution that we have in the Zulip tests, and again, it's open source, so you can go see this for yourself and copy paste it. I call it await fake async, and use it very, very similarly, but now you can go ahead and say await. I'll flip back and forth. All you change is instead of fake async run, you say that, and it finishes, and that await will finish just like it normally would in real life. And then your next assert will run, and if it's bogus, you'll find out. And here's a very oversimplified sketch of what it looks like, which is very simple. You just do again the fake async and run it, but one more step. You got to flush timers, and it looks so simple here. You could inline it, but the real thing is more complicated because you want to properly report the errors. The whole point of the test is something's going to fail, right? So it's going to throw exceptions. You want to see those exceptions properly. So probably report the errors. It's more code than this. It's not that much code. It's 20 lines. Again, copy pasted for me. If you're using it, let me know. Maybe I'll publish it as a library. That's where you can find it. Test fake async.dart in, again, the Zulip Flutter tree. And one more thing to tell you about, a different library that's also from the Dart team. You probably most of you use expect, the venerable expect, to compare what you expect to otherwise. This is what's used in the Flutter tree. It works great. But suppose you're writing you've probably had this experience. You're writing a test that's going to use it, and you expect like some finder, and what do you put there? And how do you discover what should put there? How do you discover the things that could go there? And if you're accustomed to using an IDE for everything else, like you're used to dots, and it prompts you with all the things that are the right that have the right type, and that doesn't work. That doesn't help here, because expect, it takes type dynamic for that parameter, and it kind of has to, even the way the API is written. And if only this API had types in it. One of the great strengths of Dart, it's got types. It's got real types. They're sound types. The type checker means it when it says that the thing passes. But this API doesn't. And so today, there's a typed version or type successor alternative to expect. And again, it's from the Dart team. It's called package checks. And you just write it. It doesn't look that different. You say check and the actual thing, and then you can call a method. And now, the thing has got a type, and it's a meaningful type. And that type has got methods. They're actually extension methods when you start digging into it. But that means the IDE can prompt you, just like normal, with the appropriate things to start from. And not only can the IDE prompt you, but after you've written it, the code is easy to understand. It's easy to understand for human readers and for computers. The analyzer, like we were seeing, your IDE, if you use an AI, those work better, and they got more data to work with, and more well-structured data. And that's what types give you. So that's package checks. It's a type successor to expect. And I've only scratched the surface. It's got a bunch of other features that I'm very happy with as well. And it is fully back compatible with matchers that are designed for expect. I recommend the package flutter_checks. That's what we use. So that's what I have. Again, you can see all of this in action in the Zulip code base, github.com, Zulip Flutter. And now it's time for Q&A. But if you're talking to me after this talk, you can also ask me about migrating for Activated, which we just did. We just launched our Flutter replacement. Or about getting changes into Flutter upstream, which I've gotten a few dozen in and coached other people to do so, reviewed PRs. I'd love to talk about that. That's it. All right. I think we have time for maybe a question or two. Question. Yeah, is there a microphone? If you can go to the mic.
Hey, my name is Satya. I'm at SoFi. So we use record and playback tools for the async data or the data in integration
if you speak
tests.
a little closer to the mic.
Really?
Yeah.
Okay.
It's so noisy in here.
We
Great.
use Macoon to do the record and playback. So for the integration test, I think you are hard coding JSON. So Macoon is like, you do the same. It's like in the olden days, there's VCRs, right? In Ruby, there's a VCR. So you record the network and then you store them and then you replay back.
Yeah.
Yeah. So do you see any pitfalls with that?
Yeah, that's a good question. So just to summarize, so you use a library, I think you said Mako, that for that server API, for mocking that out, it records real requests and real responses in the JSON there, and then you can use that in your tests. And the question is, do I see any pitfalls in that? So I would say first, do you have those in source control? I would definitely want to, and so it sounds you do. So I wouldn't say exactly any pitfalls in that. Definitely put them in source control. You want to know when those change. I think if you have a lot of those proliferate, if you got 80 different tests and 80 different recordings of requests they make, it could maybe become a little tough again to see what the narrative is of a test that's using one of those. And I don't know exactly. You may have solutions to this, but I think a pitfall that is possible is for it to become difficult to see out of the 80 things there, which are the bits that matter, which are the bits that the test is about, and when for example, when something changes and it's going to make a different request. Because you changed something about what this button should do, and so it's going to make a different request to the server to do the different thing you want the button to now do. Then it's important for the person making the change to be able to tell what is that change right, or what should the change be, and And I think that's potentially a pitfall that if it's purely, well, here's a recording of a request that somebody made a year ago when they last wrote this test, like it could be hard to tell that. Yeah. We definitely benefit from a good spec that's constantly evolving for our API that's constantly kept up to date. I'm very grateful for our server team taking good care of that and communicating with us and making changes. And so we have that benefit. I know not all teams will. And so we're quite content basically to write the code and also the test helpers and so on against that spec. That helps.
Yeah.
Another question? Anybody else? I guess that's it. I think it's time.